Now this is another type of full wave rectifier circuit. Let's see how does a full wave bridge rectifier circuit works. I will try to use a simple language. Dear students, on the left hand side of the figure as shown in the figure in the slide, notice an alternating current. Generally it is the secondary side of a transformer. The alternating voltage has a positive and a negative polarity. When the input is in its positive cycle, it forward biases diode D1 and D2 as shown in the figure. These two diodes conducts and current flows through diode D1 through the load through D2 and goes back to the source. It completes its first cycle. For the complete positive cycle, or when the source voltage is higher than the diode forward biased diode voltage drop, the anode of D1 is directly connected to the source. Its cathode being low, D1 is forward biased. Same applies for the diode D2. Its cathode being connected to the negative side in the current cycle of the source. D2 is forward biased. When the input is its negative cycle, D3 and diode D4 are now forward biased just like it was for diodes D1 and D2, and they conducted. For each positive and negative cycle of the source, two diodes conducts, two diodes are off at the same time. Therefore, accepting a voltage drop of 0.7 volt per diode, there is a maximum of 1.4 voltage drop in each cycle. Why? Because now there are two diodes. So the voltage drop of each diode is 0.7. So if we add both voltage drops of both diodes, so it becomes 1.4 voltage drop in each cycle. The waveform in bluish color shown below the circuit explains what you would see with an oscilloscope at the cathode of D3 or D1 or across the load if the capacitor was removed. So you see the resultant output waveform without capacitor and with capacitor. And if we use the capacitor for the action of the capacitor, I think images is self-explanatory. It shows now there are ripples when we use capacitor, which is shown in the resultant output waveform. Now in this full wave bridge rectifier, it works same as the full wave center tape rectifier. But what we want to see, what is the main advantage of the bridge rectifier upon center tape full wave bridge rectifier. So in this type of circuit that produces the same output waveform as that the full wave rectifier circuit which is shown above in the previous slides is that of the full wave bridge rectifier. This type of single phase rectifier uses 4 individual rectifying diodes connected in a closed loop which is called bridge, which is known as bridge configurations to produce the desired output. The main advantage of this bridge circuit is that it does not require a special center tape transformer, thereby reducing its size and cost. So this is the main advantage of using bridge in place of center tape full wave rectifier. The single secondary winding is connected to one side of the diode bridge network and the load to the other side as shown in the figure. Now let's see the working of diode bridge rectifier. So in this case we see in positive half cycle. In the figure, the four diodes labeled D1 to D4 are arranged in series pairs with only two diodes conducting current during each half cycle. During the positive half cycle of the supply, diodes D1 and D2 conducts means in forward bias and in series, while diodes D3 and D4 are reverse bias and the current flows through the load as shown in the figure. Means in the positive half cycle only two pair of two diodes D1 and D2 only conducts and the other two D3 D4 are open circuit due to they became reverse biased. Now in the negative half cycle, during the negative half cycle of the supply, diodes D3 and D4 conducts in series, but diodes D1 and D2 switched off as they are now reverse bias. The current flowing through the load is the same direction as before, as the current flowing through the load is unidirectional, so the voltage developed across the load is also unidirectional. The same as for the previous two diodes full wave rectifier. Therefore, the average DC voltage across the load is 0.637 V max. Now here is a typical bridge rectifier. There is a type of bridge rectifier which is shown in the slide. During each half cycle, the current flows through two diodes instead of just one, so the amplitude of the voltage, output voltage, is 2 voltage drops, means 2 into 0.7 is equal to 1.4 less than the input voltage. As I have already discussed in previous slide that in bridge rectifier the voltage drop due to two pair of diodes is 0.7 into 2 is equal to 1.4, which is less than the input V. Next, maximum amplitude. The ripple frequency is now twice the supply frequency. For example, 100 Hz for a 50 Hz supply or 120 Hz for a 60 Hz supply. It means the ripple frequency is now twice the supply frequency. We can use 4 individual power diodes to make a full wave bridge rectifier. Now in this figure is a pre-made bridge rectifier. Components are available off the shelf in a range of different voltage and current sizes that can be soldered directly into a PCB circuit board or be connected by spade connectors. The image to the right shows a typical single phase bridge rectifier with one corner cut off. You see in the figure there is a one corner which is cut off. This cut off corner indicates that the terminal which is nearest to that cut off corner is the positive or the positive output terminal or the lead with the opposite diagonal. Now the opposite of this lead being the negative or the negative output lead. The other two remaining connecting leads are for the input alternating voltage from a transformer secondary winding. Now let's have a look after the completion of our lecture number 5, what are the course learning objectives which we completed in this lecture. What is the half wave rectifier circuit and how does it works? what is a center tape full wave rectifier circuit and how does it works, and what is a full wave bridge rectifier circuit and how does it works, advantages and disadvantages of all these rectifier circuits. Thank you.